This is part 4 of the electrolysis topic on GCSE AQA chemistry. It's a dual and triple award topic, so everybody will need to cover it. And in this final section, we're going to look at what happens if we electrolyse an aqueous solution rather than a molten solution. So all of the previous videos, we've looked at what happens when we melt, for example, zinc chloride. But here, we're going to use salt solution, sodium chloride dissolved in water. So we are going to predict what the differences will be and when there will be differences. And we're going to learn about some of the very specific chemistry of the electrolysis of aqueous sodium chloride. So let's deal with sodium chloride here, brine. Brine is salt water, so it's sodium chloride dissolved in water. Have a think about what you think may be attracted to which electrode based on your prior knowledge of electrolysis. Now, the immediate thought is probably that the positive sodium ion will go to the negative electrode, the negative chloride ion will go to the positive electrode, the anode, and we will end up making sodium and chlorine. And if this were molten, that would be the case, but it isn't. In aqueous, there is a difference. Now let's break it down and try to work out why. Within salt solution, we have got NaCl and we've got H2O. Now, NaCl is made up of Na plus ions and Cl minus ions. And if we take a look at water, we know from previous experience that water breaks down into H plus ions and OH minus ions. And arguably you could end up with an O2 minus ion as well, so I've included that. Now, if we then take a look at the potential products, we could make sodium from sodium ions, chlorine from chloride ions, hydrogen from H plus ions, and oxygen from oxide ions. And we can break this down even further because we know positive ions are always attracted to the cathode. So the cathode, we could be making either sodium or hydrogen. At the anode, we could be making either chlorine or oxygen. There are actually 3 products that we make within this electrolysis process. We do make hydrogen, we do make chlorine, but we also make sodium hydroxide. Now, there is a practical that goes with this, and you can see here that we have got an electrode, we've got a circuit going on around here, we've got salt solution, we've got the electrolyte, and we can see bubbles of gas forming in both electrodes. Now, you might see this drawn in a different way. Often in schools, you will see a setup like this, where there is a tub with electrodes poking through the bottom of it. And as you complete your circuit, we get the bubbles of gas rising up and being collected in the test tube, just as we're seeing here actually. We need to label it, obviously. So we've got our brine test tube, we have our container, we've got the anode, and we have the cathode. We don't need to label the cell because we're using standard symbols down on the electrical circuit. So in terms of the method, you can see there are a number of things that we're doing. We've got the setup that I've just described, but we've also got some tests. Pause to take a minute to read through and then move on and try to answer the questions that follow. So there was a section where we added damp litmus paper to the test tube at the positive electrode. Why did we do it? What did we see? What gas did it prove was there? Well, actually, what you see when you do this is that the damp litmus paper was bleached. It goes white. It may initially, very fleetingly, go red, but then it's bleached white. And why is that? Well, that's the test for chlorine. It's showing that chlorine is being produced at the positive electrode. You will need to know that. We're going to talk about the equation in a moment, but you're also going to need to know the test for chlorine to prove that that was made there. Let's move to the negative electrode. We're inserting a lit spill or lit splint. What did we see? What does it tell us? Well, at the negative electrode, if you insert a lit spill or splint, it explodes with a squeaky pop, which is the characteristic test, the standard test for hydrogen. So we know we're making chlorine gas at the positive electrode. That makes sense. Chloride ions are negative. They're attracted to positive. They're then oxidized to become chlorine. And we also know that hydrogen, the positive ions, are attracted to the negative electrode where they are reduced to make hydrogen gas, which we can prove by inserting a lit splint and it will explode with a squeaky pop. But we've still got this solution. We place indicator in that solution, maybe universal indicator paper. What do we see? What we see is that we'll turn blue or purple, and that tells us that there is presence of an alkali. And actually, it's a very specific alkali when we do the electrolysis of sodium chloride solution, or the electrolysis of brine. We've made NaOH. So that's our third product. We need to know what the three products are, where they are made, and how we can prove that they were made. Now we need to do the equations for them as well. We now know what was made at each electrode. So let's have a look at the anode. Cl- goes on to become Cl2. I need two Cl- to do that, and I now need to balance the half equation with electrons to balance the charge. So I'm actually going to add 2E- on the right hand side. That means electrons are being lost, and that means we're dealing with oxidation. If we then think about the cathode, where we know that hydrogen was produced, we start with the H+ ions being attracted. The H+ ions will make H2, so I need to balance that. I have 2H+, and again I need to balance charge. This time I do it by adding 2 electrons on the left hand side. And that is reduction, because I've gained electrons, and you can also see I've now added my state symbols in. I'm starting with aqueous solutions. I know that chlorine is a gas, and I know that hydrogen is a gas. Now there's one added complication here, because this will happen with some aqueous salt solutions, but it won't happen with other aqueous salt solutions. Pause and have a read of this. Have a go at answering the questions. So we saw there that we didn't make sodium, we made hydrogen at the electrode. We're given the information here: if a metal is more reactive than hydrogen, the hydrogen will be attracted to and reduced at the negative electrode. So a more reactive metal, we make the hydrogen. But if we have a metal that's lower in the reactivity series than hydrogen, then we will actually reduce the metal, not hydrogen. So you can take a look at a copy of the periodic table, or the reactivity series, and you can see that really there are 2 or 3 metals that would be reduced even in aqueous solution. We would make copper, we would make silver, we would make gold. All of those 3 are below hydrogen in the reactivity series. In terms of ones where we would make hydrogen, it's absolutely any of the metals that sit above hydrogen in the reactivity series. That takes us to the end of this video and the end of this topic. Thank you for listening, and goodbye.